Hi, my name is Ashwin and I am from the NUS HCI lab in the National University of Singapore. I am pleased to present our recent work which explores the use of optical head-mounted displays for video learning on the go. Today, we perform a wide variety of tasks that require us to access information on the go, be it texting or even watching videos. Recent studies suggest that this is also the case with learning, with many users adopting mobile learning. Current explorations of mobile learning, however, have largely focused on language learning tasks that rely on static pictures and text. But with the popularity and benefits of online learning videos and MOOCs, we ask whether it's possible to view and learn using more dynamic content such as videos on the go. Prior investigations using smartphones or iPods for on-the-go video learning found it to be quite difficult, mainly because our attention is divided between learning and the environment. How then can we support video learning on the go? To better understand the situation, we interviewed and surveyed users, asking them about their motivation to watch videos on the go and the difficulties they face doing so. We found that in on-the-go situations, many users did not use their smartphones for visually demanding tasks. However, a significant number of users had personal needs or goals, such as learning for an upcoming test, which motivated them to continue their learning on the go. But users mentioned that using smartphones to do this decreased their situational awareness, as they had to maintain a heads-down posture and frequently shift their attention between the display and surroundings. To overcome some of these shortcomings of smartphones, we consider the emergent Optical Head-Mounted Display platform, which can be used in a heads-up manner and has a see-through display. These benefits make OHMDs a potential alternative platform for on-the-go video learning. Yet, viewing digital content alongside the environment in OHMDs can also distract users, making it harder to focus on the video. Existing videos may not suit the OHMD platform as they require focused attention. Hence, we investigated how video content should be presented on OHMDs. We found that a new presentation style is required for on-the-go acquisition of dynamic information on OHMDs, called LSVP, which stands for Layered Serial Visual Presentation. Let's take a look at a short clip which demonstrates what LSVP is and why it is better for video learning on the go.
Or we see actual lungs in a human being is that the left lung is shaped differently and it even has less lobes.
We found that by using LSVP on OHMDs, we were able to achieve better learning without compromising on users' walking speed as compared to using smartphones. So how was LSVP created? Well, we started by investigating 3 potential techniques that can help balance users' learning and walking using OHMDs. The first technique is highlighting, which varies the salience of an object to guide users' attention to it. The second technique is sequentiality. This also directs users' attention, but here it is the sudden appearance of the object which guides it. The last technique is data persistence, where the information that appears on screen is maintained throughout the video. This can help reduce the temporal load on users' working memory. We incorporated these techniques into real educational videos and tested it on an Epson BT300 OHMD by asking users to learn from the video while walking on a straight path. We found that data persistence and sequentiality are important for presenting information on the go, and combining both can improve recall, recognition, and walking speed of users. Finally, we compared this new design with the traditional one on 2 mobile platforms, that is, smartphones and OHMDs, to understand how the platforms compare in enabling on-the-go learning. We also considered 3 different mobility scenarios that users have to walk on: a simple straight path, a slightly more difficult curved path with obstacles, and a highly challenging navigation task which required users to walk by following direction boards. We found that users' immediate and 7-day delayed learning scores improved when using LSVP-based videos on OHMDs than with phones. This could be because users are able to switch their attention more efficiently using OHMDs, and the LSVP design complements this by guiding users' attention and reducing the impact in case users miss information. It also improved users' walking speed in the more difficult navigation scenario. This work serves as one of the first steps in our ambitious vision towards heads-up computing. As a more human-centered approach, heads-up computing aims to seamlessly blend our computing needs with our daily activities. Crucially, it aims to support this using intuitive interactions that match our natural movements. However, there is much left to explore in the LSVP, including testing to see if the results extend to outdoor settings. Additionally, while data persistence is crucial, it can lead to clutter for longer videos, and this needs to be further investigated. Thank you.